Good afternoon, dear students. This afternoon, we will look into Greek geometry and Greek mathematicians after Euclid. Now, going back to Greek geometry, the geometry, that branch of math, was the first branch of math to become highly developed. The concept of theorems, proofs originated in geometry. And most mathematicians until recent times were introduced to their subject through the geometry in Euclid's Elements. Now, these are accepted to be mathematical truths, so we don't have to justify or prove. Their role is very similar to that of the undefined terms in geometry, like your lines, planes, points. Axioms are generally statements made about real numbers, sometimes called algebraic postulates, or the properties like your properties of equality. Okay, often they say about real numbers, and it also holds true to geometric figures, since real numbers are an important part of geometry when it comes to measuring the figures. So when we speak of angle, we quantify it in terms of its measurement. For a line segment, in terms of its length. Okay? Postulates are generally more geometry-oriented. So axioms are more related to properties of real numbers. Postulates this time are more geometry-oriented. They are statements about geometric figures and relationships between different geometric figures. Sometimes they call it common notions, postulates and common notions. Of Euclid rather contains both postulates and common notions. I think we made mention of this last time. Okay, once again, the common notions are the following. Things which are equal to the same thing are equal to one another. If equals be added to equals, the wholes are equal. If equals be subtracted from equals, the remainders are equal. Things which coincide with one another are equal to one another. And number 5, the whole is greater than the part. These are considered common notions. Now, the common notions of Euclid are in fact related to our current concept of equivalence relation. If you have encountered equivalence relation in your previous math subject, an equivalence relation is a relation such that it satisfies 3 conditions or 3 properties. The property of reflexivity, reflexive property, the property of symmetry, yan, the 3 properties should be met in order that a relation is considered equivalence relation, and the property of transitivity. So it says here that common notions 1 and 4 define what we now call equivalence relation. Okay, buti na lang may taga-troubleshoot. Okay, kita nyo na. So the equivalence relation has the following properties: reflexive property, symmetric property, and the transitive property. All came from the common notions of Euclid. Equivalence relations. Later, when you get to studying sets, logic and set theory, you will encounter this relations, equivalence relations, and even in number theory. I think that's for next semester. How to prove whether a given relation is equivalence or not. So it has to satisfy these properties. Okay, so it says here that this came from common notions number 1 and 4 of Euclid. And equivalence relation is denoted by this, defined by the properties symmetry, reflexivity, and transitivity. So it's not just equal sign, but this one. Okay, so equivalence relation. Now the axioms are, from the axioms we could derive the properties of reflexivity. Yan, any quantity is equal to itself. The property of transitivity. So, review lang ito. Review of the properties of your real numbers. Ito, transitive property. Then you have substitution. If two quantities are equal, then one can be replaced by the other in any expression. The result won't be changed. Then partition, a quantity is equal to the sum of its parts. APE, MPE also have subtraction property of equality, multiplication property of equality. What do we mean by APE? Okay, addition property of equality says when two equal quantities are added, their sums are equal. Two or more. And in fact, that applies also to multiplication, also to subtraction and division. So that one allows us to add equations, subtract equations, multiply equations, and divide equations, or adding a constant on both sides of an equation, subtracting a constant on both sides of an equation, and dividing and multiplying. Okay? Next, how about your properties of inequality? Again, just a review. You have also transitivity. If there is transitivity of equality, meron ding transitivity or transitive action for inequality. If A is less than B and B is less than C, then A is less than C. Yes, transitive property yun. If A is less than B and B is less than C, then A is less than C. For example, 3 is less than 4, correct? And 4 is less than 5. Therefore, 3 dots, 3 is less than 5. That's your transitive property of inequality. Next, substitution axiom. Merong substitution. So it says here, if two quantities are equal, then they can replace each other in any inequality. So if two triangles are congruent and a segment is greater than a side in one triangle, that segment is greater than the corresponding side of the other triangle as well. Next, we also have partition axiom. We also have partition axiom for equality. Partition axiom for inequality, the whole is greater than any of its parts. But for equality, the whole is equal to the sum of its parts. Next, some additional postulates. What about postulates? Postulates are basic structure from which lemmas, theorems are derived. The whole of Euclidean geometry, for example, is based on 5 postulates known as Euclid's postulates. So, we have postulate number 1, to draw a straight line from any point to any point. From any point to any point. Number 2, to produce a finite straight line continuously in a straight line. To describe a circle with any center and distance. That all right angles are equal to one another. If a straight line falling on two straight lines makes the interior angles on the same side less than 2 right angles, the straight angle, if produced indefinitely, will meet on that side on which the angles are less than 2 right angles. Some other postulates. Through any 2 points, exactly one line can be drawn. Okay, so exactly one line can be drawn. So if I have 2 points here, no other line could be drawn containing those points. No other line could be drawn containing those points. Next, 2 lines can intersect at either 0 or 1 point, but not more than once. Okay, so if we have 2 lines, they may intersect at once or never intersect at all. Okay? For Euclidean geometry, 2 lines never intersect. And how do you call those lines? Parallel lines. Okay? If the 2 lines never intersect, we classify them as parallel lines. But for non-Euclidean geometry, two parallel lines can intersect. Now, through a point, not on a line, exactly one point can be drawn parallel to the first line, the parallel postulate. Then, through a point on a line, exactly one line perpendicular to the first line can be drawn. So, here for the previous postulate, if we have a line here and a point here, then only one line, sabi niya, exactly one line can be drawn parallel to the first line. And then number 4 says, through a point on a line, exactly one perpendicular to the first line can be drawn. So through a point on a line, there is only one. Okay, there is only one perpendicular line that could be drawn from to the first line. Okay, number 5, through a point not on the line, exactly one line perpendicular to the first line can be drawn. A segment has only one midpoint. Yes? Okay, an angle has exactly one bisector. These are postulates. We don't have to prove them. They are accepted as general truth. The shortest distance between 2 points is the length of the segment joining those points. Now we proceed. Some other features of Greek geometry are the following. So aside from the postulates and the axioms, okay, from which come the theorems, okay, and proofs, the deductive method, another feature of Greek geometry is regular polygon or the regular polyhedra. So from them came the concept of regular polyhedron or polyhedra. What is a regular polyhedron? Okay, by definition, a polyhedron is bounded by number of congruent polygonal faces so that the same number of faces meet at each vertex, and in each face all the sides and angles are equal. Okay? The faces are regular polygons. And if the faces are regular polygons, then it is a regular polyhedron. Okay? A regular polygon, what's your understanding of a regular polygon? What is a regular polygon? Are all polygons regular polygons? Okay, what's a polygon, by the way? And what is the difference between polygon, regular polygon, and just a polygon? Okay, polygon, regular polygon. Regular polygon has congruent sides and angles. Yes, just like your square. Square is a regular polygon. Your equilateral triangle is also a regular polygon. The sides are equal or congruent, and the angles are also congruent. So that makes it a regular polygon. Now, regular polygon for any n, okay, greater than 2 number of sides. Okay, number of sides like n greater than 2 means 3. So a triangle, and then a square, pentagon, and so on. But what is a polyhedron? A polyhedron is that which is bounded by congruent. So if I have squares, then if I have squares, okay, I will connect them such that there will be how many vertices? Okay, 1, 2, 3, 4, 5, 6. Okay, so what will we come up with? It's a cube, yes? It's an example of a regular polyhedron. A polyhedron is bounded by congruent polygonal faces. Okay, so the faces are squares, 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 square, squares. How many squares are there? 6. Okay, the same number of faces meet up at each vertex. Okay, so the meeting is the vertex, and each face, all sides and angles are equal. And therefore, we call it a regular polyhedron. So, two conditions must be satisfied. The faces are equal, and the angles formed at the vertices must be equal. There are only 5 regular polyhedrons. And what are they? What are the regular polyhedrons? The regular polyhedra, the 5 of them are your cube, like what I said a while ago. The faces are, or the surfaces, okay, the faces are squares. Okay, cube, the tetrahedron, the octahedron, the dodecahedron, icosahedron. So Greek geometry made some impressive discoveries and managed to complete one of the most beautiful chapters in solid geometry, the enumeration of the 5 regular polyhedra. Okay, the 5 possible regular polyhedra are this, nothing more. Okay, the cube, the tetrahedron, octahedron, dodecahedron, and icosahedron. So your tetrahedron is made up of how many triangles then? Kung tetrahedron siya, 1, 2, 3, 4 triangles. Okay? So 4 equilateral triangles. Yan. With how many vertices? If you could imagine, okay, 1, 2, 3, and the top, which is the 4th. So for a tetrahedron, there are 4 vertices. How many edges? 6 edges and 4 faces. Okay? Edges are this: 1, 2, 3, 4, 5, and 6. Okay? Those are the edges. When we speak of faces, ito, this part. Okay? One triangle, another triangle, third triangle, fourth triangle. So, how many faces? 4 faces and 6 edges. Okay? The faces are all equilateral triangles. This is a tetrahedron. The next is a cube. And you know very well a cube. So your cube has, yes, 1, 2, 3, 4, 5, 6 faces, squares, okay? So 6 faces, how many vertices? 8 vertices rather, 4 on top, 4 below, so 8 vertices, and 12 edges. 12 edges because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 edges. Next, we have the octahedron. Okay, octahedron. There are 8 faces, 12 edges, and 6 vertices. Okay, next, we have the icosahedron consisting of 12 vertices, 30 edges, and 20 faces. And finally, the dodecahedron consisting of 20 vertices, 30 edges, and 12 faces. 12, dodeca. Okay, dodeca, the prefix dodeca is 12. So 12 faces. Octa from 8. Okay, 8. Octahedron. Icosahedron, 20. Okay, cube. And the tetra for 4 faces. And we consider this the Platonic solids, which are representative of the 4 elements. So, according to Plato, the fire, okay, tetrahedron for fire, okay, the universe, cube is earth, and then we have dodecahedron, the icosahedron for the universe, air is for octahedron. Okay, so each Platonic solid represents an element, and the corresponding elements are fire, universe, earth, water, and air. We call them the Platonic solids. Now, the proof that there are only 5 regular polyhedra. So we considered polygons that can occur as faces. Okay, faces, and the sum of the angles with common vertex must be less than 2 pi, which is 360 degrees. And, okay, If the number of sides is n, 3, okay, the angle, diba? Every angle of an equilateral triangle is, if it's equilateral, equal sides, then the angles must be equal also. That's 180 divided by 3, yes? Or 60 degrees. So the maximum number of faces could be, okay, 3, 4, or 5. When the side is 4, so 4, and that's square rather, the vertex angle of a square is 90 degrees. Yes, 90 from 180 divided by 2. Okay, maximum number of faces ay 3. For 5, 3 pi over 5, 3, 6 and more, it's impossible. So, there are only 5 regular polyhedra. So, now, each polyhedron is convex. Polyhedrons are singular, polyhedra for plural. Convex and is bounded by a number of congruent. Okay, what do you understand by the word convex? And differentiate it from the word concave. Okay, convex versus concave. Okay, convex versus concave. What's the difference between the two? Now, let me draw two figures, and I'd like you to identify which figure shows concave polygon and convex polygon. Okay, A versus B. Okay, in which figure is the polygon a convex polygon? And in which figure is it concave, A or B? Okay, A or B? Anyone? Convex? Which one? Just tell me the letter. Convex is A or B? Which one is convex? Which one is concave? A is convex. O, dalawa na. So, two of you said letter A is convex, and therefore, letter B must be concave. So, what then is the difference between the two? What is the difference? When is it concave then? Okay, what can you say about letter A and contrast it to letter B? So that from here, we could distinguish between convex and concave. Okay? Let's look into the diagonals. So from there, we could differentiate between convex and concave. Okay, what is a diagonal, by the way? Diagonal of a polygon is a segment joining two non-adjacent vertices of a polygon, isn't it? So that if I draw, okay, this line segment, okay, this is a diagonal of the pentagon. Okay, this is even a diagonal of the pentagon. Where else? Ito, this is another diagonal of the pentagon. This one is another diagonal of the pentagon. Now, let's contrast it to letter B. Now, this one, let's connect these two non-adjacent vertices of the polygon in B. Okay. Here, I could even draw from here to this one. From here to this vertex. But I can also have one here. So, anyone who could? Convex has a total angle of 180 degrees. Okay. So from here, from the illustration itself, what can you say then about convex and concave in terms of the diagonal? Diagonal. What did we draw? Diagonal. Okay, so may klarong relasyon, di ba? So that from here, we could easily say diagonal, by the diagonal, whether a polygon is concave or convex. Okay, someone said all diagonals are inside. Okay, so for convex, sabi niya, all diagonals lie entirely inside the polygon. You're right. Okay? So for convex, okay, so let's write that here so you won't forget. Convex, all diagonals lie entirely inside. Okay? Inside the polygon. Otherwise, it's a concave. Okay? Convex versus concave. So I think that's clear now. So letter B is really concave. So going back to our polyhedron, so when we speak of a polyhedron, then it is formed by simply enclosing a portion of a three-dimensional space, okay, with four or more plane, okay, polygons. Okay, is there with four or more? Let's go back. Okay, four or more. Okay, is there a polyhedron with three faces only? Okay, not possible. So the simplest is this. Okay, the simplest is your tetrahedron. So once again, a polyhedron is formed by enclosing a portion of a three-dimensional space with four or more plane polygons. So your tetrahedron is made up of four regular triangles. Now we proceed to the next. So we're done with this, convex and concave. Now, this is an example of a polyhedron. However, it is not regular. Remember our definition of a regular polyhedra? Okay, bounded by congruent polygonal faces. Okay, obviously, these faces here are not congruent to this. So, this is not a regular polyhedron. It's simply a polyhedron. But this one is a, polyhedron. Next, polyhedron. So, construction of an icosahedron by Luca Pacioli in 1509. It consists of three golden rectangles. Can you identify the three rectangles here? So, he made use of three rectangles intersecting. Actually, intersecting rectangles. Can you see that in the figure? This is the first rectangle. I may label it as R1. So, this construction by Luca Pacioli in 1509 made use of three golden rectangles. This is R1. Ito. From here, I hope you can see it. Yan. Yan. That's R1. And then R2, ito. And where is the third then? Third is the rectangle along the center. Okay, so they are intersecting golden rectangles and the dimensions are as follows. Next, Kepler also had his own version of the polyhedra. So Kepler in 1596 theory of planetary distances, and aside from that, his laws of planetary motion. So your Kepler's theory is summarized by the famous diagram of the 5 polyhedra nested in such a way to produce 6 spheres of radii proportional to the distances of the 6 planets then known. So this is the diagram of Kepler. So Johannes Kepler, some of his important contributions are the laws of planetary motion, Kepler's theory of planetary distances based on the regular polyhedra. However, the theory was ruined when Uranus was discovered in 1781. Now, spheres. Now, for every regular polyhedron, there exists the sphere which encompasses or which passes through all the vertices. Okay? Its radius is called the circumradius. Okay? Radius of the sphere. Okay? And the sphere, the sphere which touches all the faces, rather, its radius is called the in radius. So there are two spheres. One sphere, okay, passes through all the vertices. And the other sphere passes through all the faces. You get it? Ito, let's go back to the simplest. Okay, the sphere that passes through all the vertices, okay, and the sphere that touches all the faces. So there are two spheres here, therefore there are two radii that we are looking into. So what's the difference between circumradius and inradius? Yan, the circumradius is the radius of the sphere which passes through all the vertices. Whereas inradius, okay, inradius is the radius of the sphere that touches all the faces. Take note that face and vertex are different. So you go back to your Platonic solids. Let's go back to our Platonic solids. These are the vertices. Okay? And these sides are the faces. So merong sphere daw that could be drawn that touches all the vertices. And in like manner, there is a sphere which could be drawn that touches all the faces. Ang tawag sa radius nito ay circumradius. Yung nasa loob ay inradius. Ginamit no Kepler kasi yon. Okay? So, Kepler made use of that in his computation. Circumradius over inradius. So, the ratios between successive radii in Kepler's construction depend on what we call it inradius and circumradius. The radii, okay, that's it. That ratio is the same for the cube, the octahedron, and also the same for dodecahedron and icosahedron. What does it imply? It implies that the cube and octahedron can be exchanged in Kepler's construction, as can the dodecahedron and icosahedron. Thus, there are at least 4 different arrangements of the regular polyhedra that yield the same sequence of radii. So, this ratio is constant daw. The same value for a cube and for octahedron, and in like manner, same value for dodecahedron and icosahedron. So, that's about the circumradius and inradius. Now, another feature of Greek geometry, ruler and compass constructions. There are 3 great problems in Greek geometry. The 3 famous problems are the problems of doubling the square or squaring doubling the cube rather. Okay, duplication of the cube. Look at their problems. Duplicating the cube, trisecting an angle, and squaring a circle. But prior to that, let's go back to the previous slide. Okay, some elementary constructions or operations with the ruler and compass. Okay, given 2 points, we can construct a line through them. Given 2 points, we can construct a circle centered at 1 point, passing through the other. Okay, given 2 lines, 2 circles, or a line and a circle, construct their intersection points. Now, the 3 famous problems in ancient Greek geometry are or deals with duplicating the cube. What does it mean? For a cube with a given volume, can you construct another cube whose volume is double the original using only a straight edge and compass? Okay, so that's one problem. That's one problem, a famous problem in ancient Greek geometry. Another problem is that of trisecting an angle. Now, it says here that although it's difficult to give accurate date as to when this problem appeared, Hippocrates, who made the first major contribution to the problem of squaring a circle and doubling a cube, studied the problem of trisecting an angle. And there is fairly straightforward way to trisect any angle, which was known to Hippocrates. And the third famous problem is squaring a circle. What do we mean by squaring a circle? What is it all about? What is this problem all about? To square means, okay, given a geometric figure such as triangle or circle, construct a square whose area is equal to the area of the given figure. So that is the meaning of squaring a circle. Next, equivalent forms of those three problems are the following. Yan, duplicating the cube. Okay? Geometrically representing cube root of square root of 2. Okay? The looking for exact value of pi, then trisection of the angle alpha, okay, by showing sine 20 degrees. Okay? Next, some other open problems in Greek geometry are the following. Which regular n-gons are constructible? Okay? How do we divide a circle? Okay, in 1796, Gauss, okay, constructed a 17-gon. Okay, so it says 17-gon is constructible and a regular n-gon is constructible if and only if it satisfies this, okay, equation, which is the Fermat prime. When you get to number theory, you will encounter more of Fermat's theorems, and in fact, you will be trying to prove some of them. Okay, and then what are the primes? Okay, primes in fact was the focus of another Greek mathematician in the person of Eratosthenes. You may have encountered Eratosthenes in your earth science. He tried to measure the distance of, okay, the moon, the sun, okay, the circumference of the earth, and so on and so forth. More on astronomy. Now, are there infinitely many of these primes? Okay, so those are some of the open problems. Another feature of Greek geometry, conics. Okay, we made mention of conic sections before, yes? Conics are the curves obtained by intersecting a circular cone by a plane. So the intersection could form any of the following: a hyperbola, an ellipse, including a circle, and a parabola. So if the plane cuts the cone, or such that the plane is parallel to the horizontal axis, then what kind of conic section is formed? A circle. If it it cuts the cone in this manner, then the conic section is an ellipse. Okay, and then here, quite slanting, this is a parabola and hyperbola. If we have two, may ganito, okay, let me show you. Okay, this is for a hyperbola. Ayan. One upper curve, this is the upper curve, and one lower curve. Okay, hyperbola, this one is an ellipse, this is, okay, a parabola. So they are sections of the cone, kaya conic sections. Okay, they are sections of the cone, conic sections. So generally, any second degree equation represents a conic section or a pair of straight lines, and the result was proved by Descartes in 1637. But the first to work on conics is another Greek mathematician in the name of Menachmus. Okay, and then later by Apollonius, who wrote a book entitled Conics. So your ellipse, okay, has the formula x squared over a squared plus y squared over b squared equal to 1. And then your parabola has the formula or the equation y equal to ax squared. Your hyperbola, look at the difference between the equation of an ellipse and a hyperbola. Okay, what's the difference between the two? This is addition. For hyperbola, we have subtraction. So you have x squared over a squared minus y squared over b squared equal to 1. So Descartes, okay, represents any second degree equation represents a conic section or a pair of straight lines. Next, also, it's Menachmus, and then later on, Apollonius. The invention of the conics, okay, we attribute or should we give credit to Menachmus rather for inventing the conic sections. And he used the conic sections to solve the problem of duplicating the cube. Remember, one of the famous problems in Greek geometry, duplicating the cube. Finding the intersection of a parabola with a hyperbola. So the intersection of the formulas or the equations y equal to 1/2 x squared and xy equal to 1. So y equal to, okay, 1/2 x squared, which gives this. Okay, so y equal to, okay, that's it. 1/2, get the intersection and equal to 1. Okay, x cubed equal to 2. So, drawing of the conic sections. Generalized compass. Okay, to draw a conic section, we can make use of a generalized compass described by the Arab mathematician Al-Khuji around 100 or 1000 CE. Some other applications of the conics, like what we mentioned a while ago, Kepler made use of it also to explain distances and later on the orbit of the planets in terms of ellipses. Yes, the planets are moving around in elliptical orbits. Yan. Orbits of the planets are elliptical. Furthermore, Newton also explained this fact by his law of gravitation. Okay, so conic sections are inventions of Menachmus once again. Okay, next, higher degree curves. There was no systematic theory on higher degree curves in Greek mathematics. The Greeks studied many interesting special cases like that of cissoid of Euclid, spheric sections of Perseus, and the epicycles of Claudius Ptolemy, but we will discuss this later. Okay, Ptolemy is one of the Greek mathematicians after Euclid that we will discuss later. The cissoid of Euclid, which looks like this. Okay, he showed that the cissoid could be used to duplicate the cube. So really, their concern is to solve the three famous problems: duplicating the cube, okay, squaring the circle, and trisecting an angle. Yan, the cubic curve with Cartesian equation y squared times the quantity 1 plus x is equal to 1 minus x cubed. This one is a cubic curve. X raised to the third is cubic. Ito yung spheric sections ni Perseus. Okay, one of the surfaces studied by the Greeks. Okay, and it looks like this. So this one is an oval, Cassini oval, lemniscate of Bernoulli. This is an example of a curve of degree 4. Kanina, a curve of degree 3. Okay, yung cissoid of Euclid. And this one, this time, is a curve of degree 4. And for Ptolemy, okay, Almagest of Ptolemy, which consists of his astronomical works. Okay, Claudius Ptolemy for a model of the solar system, if you could remember. Then epicycles, okay, planetary orbits. So he has his own version of the planetary orbits. And Kepler has his own version, which is elliptical. Next. Now we proceed to the Greek mathematicians after Euclid. We begin with Archimedes. We made mention of Archimedes already when we looked into the values of pi, history of pi. Okay, he was born in Syracuse, a principal city-state of Sicily, the son of an astronomer named Phidias. He spent considerable time in Alexandria, where he studied with Euclid's successors. It is there where he met Conon of Samos, Eratosthenes of Cyrene, okay, both leading mathematicians of their day. Now, he determined the value of pi to be between 3 and 10 over 71, between 3 and 10 over 71 and 3 and 1 over 7. How did he obtain his measurement or of this value? This value was obtained by circumscribing and inscribing a circle with regular polygons having up to 96 sides. Okay? So how difficult it is to draw a polygon with 20 sides, much more with a 96-sided polygon. And also Archimedes' law of buoyancy and his law of lever. So law of buoyancy, according to stories, he was commissioned to determine whether the crown is made of pure gold. And he actually found out that the gold, or should I say the crown, was made of pure gold when or while taking a bath, naked. And then he shouted, "Eureka, Eureka." Next, another famous Greek mathematician after Euclid is Eratosthenes of Cyrene. Okay, Eratosthenes was a Greek mathematician, geographer, poet, astronomer, music theorist. Okay, he invented the discipline of geography. Okay, geography including the terminology used today. He is best known for being the first to calculate, let me underscore, circumference of the earth, which he did by applying a measuring system using stadia, standard unit of measurement during his period. So stadia is a unit of measurement. His calculation was remarkably accurate. Okay? He was the first also to calculate the tilt of the Earth's axis. Okay? Next, he may have accurately calculated the distance from the Earth to the Sun and invented the leap day. Okay, leap year. So we have to give credit to Eratosthenes for all of these significant contributions. Next, aside from that, he created the first map of the world incorporating parallel meridians based on the available geographic knowledge of his era. Next, he was the founder also of a scientific chronology, and he endeavored to revise the dates of the literary and political events from the conquest of Troy. Now, in number theory, he introduced the sheaf of Eratosthenes, an efficient method of identifying prime numbers. Okay, we have the Are you familiar with the sift? Okay, how many are Itawid speaking from among you? Atsa. Okay, sift. Sift. The sheaf of Eratosthenes sifts, separates. Okay, so your sieve separates the coarse from the fine grains. Yes? So in like manner, the sheaf of Eratosthenes separates the primes from the composite numbers. How do we do that? Okay, so to to illustrate how to make use of the sieve of Eratosthenes. Okay, let's go back. And identifying prime numbers. How? So you list down the numbers from 2 to, let's say, we would like to identify the prime numbers less than 50. So jot down all the numbers from 2 to 50. Let's not consider one, we will not include 1 anymore. So 2, okay, to show you how it works, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, then 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, okay, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, and then 41, 42, 43, 44, 45, 46, 47, 48, 49, and then 50. So, mark all numbers that are divisible by 2. But we skip 2. So, we skip 2. I will mark or cross out the numbers which are divisible by 2. Starting with divisible by 2 or multiples of 2, so I'll strike out 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, let's strike out all multiples of 2. So next. The next unmarked number is 3. So we're done with 2, we proceed to 3. This time, we cross out or mark out all multiples of 3. Okay, excluding 3. So we begin with 6, pero tapos na, na-marked out na siya. 6, so 9, then 12, tapos na rin. Then 15, and then, which one is next? 18, tapos na. 21. And then, 24, tapos na. Then, 27. And then, 30. Then, 33. Then, after 33, 36, done. And then, 39. Then, we have 42. Now, we have 45. Okay. And then, we have 48. 48. Tama. Finished. Okay. Now, next. The next unmarked number is 5. Okay. Let me encircle. So, let me encircle this using blue. We're done with 2. We're done with 3. We're done with 5. Oh, no, we're moving on to 5 rather. So, for 5, we will, okay, cross out also all multiples of 5. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Next, the next unmarked number is 7. Okay, the next unmarked number is 7. So, from 7, we will now, okay, cross out all multiples of 7. So, the next to 7 will be 14. 7, 14, finished. 14, 21, finished. 28, finished. Okay, and then we have plus 7 is 35, finished. Plus 7, 42, finished. Plus 7 is 49. Okay, let's use another color. Okay, ito. 49. Now, 11. Okay, let's move on to the next unmarked number, which is 11. And we cross out all multiples of 11 beginning with 22. Okay, 22, nasan ka? Finished. Write out na siya. 22 plus 11, 33. 33 plus 11 is 44. Finished. So, wala na. Then we have 13. 13 plus 13, that's 26, crossed out. Plus 13, 39, crossed out. No more. Okay? Therefore, we're down to 17, to 19, to 23, to 29, 31, 37, 41, 43, and 47. So, therefore, these are the prime numbers below 50. Okay, so nasala. It's a sheaf. Sheaf of Eratosthenes. So, the prime numbers below 50 are 2, 3, 5, 7, 11, 13, 17, 19, 23, okay, 29, 31, 37, 41, 43, and 47. Okay, so this is the sheaf of Eratosthenes. Now the question is, what if I give you a quite large number, and how will you tell whether it's prime or not? For example, is 413 a prime number? Okay, is 413 a prime number? You can use divisibility test. When is a number divisible by 2? If it's even. Or if its last digit is, okay, if its last digit is divisible by 2. Okay, so it's not divisible by 2. Not divisible by 2. Is it divisible by 3? When is a number divisible by 3? Remember, if the sum of the digits is divisible by 3. So if you get the sum of the digits, 4 plus 1, 5. 5 plus 3, 8. No. Okay, so not divisible by 3. Is it divisible by 4? Okay, so not divisible by 2, not divisible by 3, not divisible by 4. Okay, obviously not divisible by 4 because the last digit is 3. Okay, when is a number divisible by 4? Wait, let me erase muna. So it's not divisible by 4. Okay, not divisible by 4. Is it divisible by 5? Is it divisible? No. The last digit is 3. Okay, the last digit is 3. It's not divisible by 5. Is it divisible by 6? No. It's an odd number. Is it divisible by 7? Okay, 4, 1, 3. So let's do it manually. 4, 1, 3 divided by 7. Okay, so 5, 35. Correct? Is it divisible by? But your answer is, it's divisible by 7. Okay? Because 413 divided by 7 is exactly equal to 59. Yes? Yes, this is exactly divisible by 7. Okay? So, answer is, yes, it's divisible by 7. So, let me write here, divisible by 7. So, is this a prime number? No. Baligtarin natin. Yes, it's 59. 59. How about 431? Kung baligtarin ko, is 431 a prime number? Okay, I want you to answer. Is 431 a prime number? Is it also divisible by 7? 431? No, it's not. 431 is not divisible by 7. Let's check. Is it divisible by 2? Is it divisible by 2? Is 431 tayo. Is 431 413 yung kanina. Baligtarin natin. Is 431 a prime number? Okay, check. Divisible by, is it divisible by 2? No. By 3? No. By 4? Okay, no. By 5? No. By 6? Not even. By 7? Okay, no. So you said it's a prime number. So look, if we keep doing this, we will be wasting much of our time. Yes? See, we keep doing this until, where should we stop? The question is, until which number? Okay, until 200, until 100. There is a technique. Okay, you perform divisibility test only up to the square root of that number. Okay, so look for integers I, okay, I less than or equal to the square root of n. Okay, less than or equal, where I is an integer. So how do we test then whether a very large number is prime or not? Get its square root. Okay, so we take the square root of 431. Get your calculators and extract the square root. The square root of 431 is equal to 20.76. So the integer, okay, the closest integer to the square root of n is 20. So you can begin with 20. That I is 20. So 20, 19, 18, 17, and so on. So umiksi, konti na lang itetest natin. Okay? So hanggang dito lang. From 20 below. So 16, and so on and so forth. So all you have to do is to continuously divide the given number, which is 431, by these numbers or by these integers. Obviously, not 20. Okay? So I will begin with 19. So get your calculators. 431 divided by 19, hindi pa rin. Okay? It's not exact. So not divisible by 19. Next, 41 divided by 18. Okay? Not exact. And then, none of these numbers. If none of these numbers, they divide, none of the numbers divide n, therefore, n is a prime number. So, answer here is, okay, yes, it's a prime number. Okay, so none of these numbers, none of the numbers 20 and below, none of the integers 20 and below divides, okay, the given number 431. Last one, how about, that's a bigger number, is wait, let me change it. Okay, prime number. I think we could stop with this problem, and the rest of the mathematicians after Euclid, I will just give it for your reading. I'm not giving any assignment because next week will be academic relief week. Okay, so let's end up with this. Is 3,121 a prime number? Is it a prime number? How about 1,200? Is it a prime number? Not prime. Ay, not prime daw. Sige, tingnan natin. So, applying the, okay, the test, okay, take, or should I say, identifying integers that could possibly divide the given number. We take the square root of 3,121. This is quite a big number. So, we extract the square root of 3,121. 3121. Square root of 3121 is equal to, konti lang, 55 point something. So, 55.87. So, I could begin with 55. So, what values will I make use of as my divisor? You can have 55 and below. Okay? Yeah, because this is 55.87. So, is it a prime number? You can, okay, let's get 3121 divided by 55, obviously, no. Then, we can skip 54 kasi this is even, this is not even. We can proceed to 53. So, strike out na lang natin yung natapos natin. We're done with 54. Let's say, do not include 54 anymore. Obviously, it's not divisible by 54. Then 53, 3121 divided by 53. No. Next, 52. Do not include 52 anymore. Okay, let's have now 51. Baka. Okay, 3121 divided by 51 equals no. So, not even 51. And then, not 50. Wag na include ang 50. Then, we can have 49. Okay, 48, no need. So, we can have 47. 46, no, it's even. No, it's not. 47, so 45. 43, 41, 39, whichever. Okay, 39, and then we can even have 37, 33, wag na, 33, 35, it's obviously hindi pwede, 35, 34, hindi, 31, then 27, okay, 29, I forgot, 29, 27, not 25, can have 23, can have 21, and then 19, 17, 13, 11, 9, 7, and then 3. So, any of these numbers could possibly divide. So, let's test one by one. 3121 divided by 49. Okay, no. 3121 divided by 47. No. 3121, bakit in-include natin si 45? Let's strike this out. Strike out. 43. 3121 divided by 43. No. 3,121 divided by 41. No. 3,121 divided by 39. No. 3,121 divided by 37. No. 3,121 divided by 31. No. And 3,121 divided by 29. Okay, next. 3,121 divided by 27. No. 3, 1, 2, 1 divided by 23. No? 3, 1, 2, 1 divided by 21. Strike out. 3, 1, 2, 1 divided by 19. Okay, 3, 1, 2, 1 divided by 19. Also, hindi pwede. So, strike out. 3, 1, 2, 1 divided by 17. So, also, okay, 3, 1, 2, 1 divided by 13. 3, 1, 2, 1 divided by 11. No. Is it divisible by 9? Definitely not. Divisible by 3? No. And is it divisible by 7? 3, 1, 2, 1 divided by 7 is, okay, so, no, it's not a prime. It is a prime number. Okay? So, it's a prime number. Okay, we end up with that. The next slides, I will give us your reading. The next slide consists of the works of Apollonius, Hieron of Alexandria, 3,000. Okay. Tama, nalobat na ang aking laptop. Okay, patay na ang aking laptop. Okay, sige. Okay, I will just upload my PowerPoint presentation or the things that we have discussed this afternoon to Lens. Okay, so no assignment. The rest are reading materials, but it's for the week after next week anyway. Other questions? So I think we could end our session now. Okay, prime number. Okay lang kasi tinapos ko na lang. Hindi, nandito yung PowerPoint ko. Lipat ko dyan. Nandun sa iPad. Ay, nandun sa MacBook.
Ano ba? Gusto mo pa ilo?
Hindi na lang. I-upload ko na lang.
Bumili ka.